Okay, we are going to cover chapter 3, vectors. So let's get to the PowerPoint. It's humid today, isn't it? Okay, vectors. They're showing a vector from Avalon, Catalina Island to Newport Beach. First, we have to discuss coordinate systems, and we're all familiar with the Cartesian coordinate system, attributed to Descartes. And so we have two specific points. P is at x equal 5 and y equal 3. So you can go up, you can go across 5 ticks of the graph and up 3, and you're at point P, 5, 3. The point Q is at minus 3, 4. So you can go to the left 3 ticks of the graph and up 4, and you're at P minus 3, 4. And then there's a general XY, and it looks like it's at x equal 3 and y equal to like 8.4, 8.3 is your uncertain number that you have studied in lab. So that's a coordinate system that we use, a common coordinate system that we use. However, there are others, the polar coordinate system, where we can define an x and y by a length r, or a radius, a radial component, and an angle theta. And they're related to each other by the y component is the sine theta. The sine of theta is y over r, and the x component is cosine theta is x over r, and then the tangent theta is y over x. And you're gonna use that there's a little mnemonic, SOHCAHTOA. Yeah, I'm sure most of you know that. I just kind of remember. I've used it for so many years. I just remember which one is which. Sine is associated with y and cosine is associated with x, but that's not always going to be the case as we do problems. And we'll see when we elevate a ramp, we're going to change the coordinate axis. So, but in general, the y is associated with sine and the x is associated with the cosine. So to get, if you have an r and a theta, you get y by saying r sine theta, and you get x by saying r cosine theta, and that'll give you the values of y and x. We'll use that quite often. As a matter of fact, there it is. X equals r cosine theta, y equals r sine theta. And the tangent of theta is equal to y over x, and r is equal to the square root of the sum of the squares, the old Pythagorean theorem. X squared plus y squared is equal to the square root of x squared plus y squared is equal to r. Now all of this refers to right triangles, where there's a 90-degree angle in one of the corners. You can only have one 90-degree angle, otherwise it's not a triangle any longer. So here's an example. The Cartesian coordinate of a point in the xy plane, xy equals minus 3.5 and minus 2.5 meters, as shown in the figure. Find the polar coordinates of this point. I don't usually go through the examples, but I'm going through this one because I think it's an important point to go back and forth between polar coordinates. So the radial distance is equal to the square root of the sum of the squares, x squared plus y squared. So that's minus 3.5 squared and plus a minus 2.5 squared. Of course, the squaring takes away the negative, and when you take the square root of that, you get 4.3 meters. And then the tangent is equal to y, the tangent theta is equal to y over x. So y over x is equal to 0.25 over minus 3.5, and that's equal to 0.714. So you take the arctangent of 0.714, and you probably won't get 216 degrees. You'll probably get something else. Let me, it's it's on my phone. So if we take the, if we take the 0.714 and take the tangent inverse, I've got 35.5. Let's make sure I got interrupted. So let's make sure that 0.714, enter, and take the arctangent at 35 degrees. So if you just enter it into your calculator as the tangent inverse, tan minus 1 is typically what you have on your calculators, of minus 2.5 over minus 3.5, you're going to get 35 degrees, 35.5 degrees. But that's going to be wrong. That's 180 degree out. So you have to know what coordinates, what quadrant your vector lies in, and this is in the third quadrant. So that's going to give you a completely different angle than what your calculator gives. Now, I don't know if some calculators do this, but certainly Excel, they have like an arctan, I think it's arctan 1 or something like that, that you can put in the actual coordinates and it'll give you the exact angle. We'll try to do some examples of that maybe in lab. Okay. Now we're gonna. I think that's it for this. We'll discuss vector and scalar quantities in the next short segment.